Hello world, hello internet, and welcome to the 10th episode of the 2023 Nix Developer Dialogues. I am Valentin, your host. My host name is Frickler Handwerk, and this show is about people and stories from the Nix ecosystem, where we talk a lot about open source and how it's made. Now, this show comes to life with your participation, so please send us your questions or comments from wherever you're watching this, or on Matrix, or come to the studio and be part of the show, ask your questions in person. If you don't know how to find that, go to the NixOS Discord, search for Nix Developer Dialogues. Everything is linked up there. And now let's welcome our guest today, Sergei Kozlukov, known as Someone Sergei. Hi. Welcome, Sergei. Thank you very much for joining. So you're working on your PhD at Aalto University in Finland. You're doing research in computer vision. And our topic today is deep learning and AI applications in Nix packages. So it's not a coincidence that you're here today. You're part of the CUDA team of maintainers in Nix packages, the mission of which is to make Nix and NixOS the first choice for users of CUDA accelerated software. And we'll talk more about what that team is doing and what you have been done and what the state of GPU acceleration in Nix packages and NixOS is. But before we do that, please tell us more about yourself by answering my first and obvious question. Actually, two questions: why and how, and who and or what got you into Nix, and why are you still here? Two questions.
Okay, so what got me into Nix is some of my mad friends, I guess, which were curious about the thing at the time. That was maybe around 2020, 2021, not too long ago. For whatever reasons, like they got me curious as well. Started looking into that, and then I think I installed NixOS after I and a couple of my friends have tried to bootstrap a dev box for machine learning bullshit, and we tried using NixOS on that, and this is what got all of my friends scared away from Nix and NixOS, and what got me into spending increasingly more time on it. So I got sold on the idea almost right away because I could see how it fundamentally solves some of the underlying issues solves the complexity that hasn't been solved with integrating like several independently evolving ecosystems like Python packages and building native extensions for Python, and then like doing all of that with the co-processor like GPU devices in mind, and then handling that in HPC environments. All of those are more or less independent ecosystems and independent communities, which may not always agree on like what is the right way to do things, and you get a lot of you don't get any divergence unless you introduce a more systemic tool. And to me, Nix seemed like it had done that to many other domains already. So I got into Nix because of that. I stayed, I guess, just because it's such a charming community.
What's different with the Nix setup as opposed to, say, conda or pip? For many people, conda just works.
Conda just works. It's true. Conda just works after you have solved a bunch of issues, like runtime issues, after you have found the correct configuration. After that, it just works. And then you try and reuse the same environment on another machine. You try to bootstrap the same environment on another machine from scratch, or you try to do the same on the same machine, but a couple of months later, and you find that actually all of those problems you have solved, you have to basically figure out again. This has to do with, I think this has to do fundamentally with how conda or classic distributions approach package deployment, which is doing things in a very dynamic manner and doing things. I want to say impurely, but that's going to sound too abstract. What's different with Nix is that with Nix, you deploy a package in a certain sense without side effects. You have packages that can be composed in environments, and when you install a package, it doesn't affect anything else in your system. It's installed into an immutable store, and you do not install it as the installation is not just fetching a pre-built artifact. You actually have a recipe that describes how to bootstrap the thing you desire from very scratch, maybe from like the Linux kernels and the libc, and that recipe in the end is realized into a very concise and precise description that contains all of the inputs that could possibly affect the output. And only after that, the build is run in sufficiently reasonable isolation to produce those outputs that can only be installed into this location that is then to be used in a read-only manner. And when we use pre-built packages with Nix, we basically check whether there is whether an output exists in the cache for this specific description, this concise and self-contained description of what it is we want to get, and only if there is a record for this concise self-contained description, only in that case we trust the system enough that actually we can reuse this cache for whatever it is we want to use it for.
So that means that when you're using software built through Nix, you just have a lot fewer moving parts.
Yes, somehow all of the moving parts, all of the moving pieces that can possibly affect the output, they are modeled within the system. You describe all of them, and it's at the same time, because you're forced to describe those things, you also tend to take care to remove the dependencies that are irrelevant. So you get better isolation and you prune the dependencies. Essentially, I would say it makes sense to treat a build as a random variable, in the sense that there are many possible states of the world that you cannot possibly comprehend all of them, and every state of the world corresponds to a different output. And with Nix, you're encapsulating you're encapsulating the states of the world that matter. You're making this random variable more deterministic, is what I was saying.
So how does that reduced randomness or increased determinism affect your day-to-day work and research? So you run enormous workloads on thousands of GPUs. How does that help?
Okay, so first a disclaimer. At this point, I'm not running any enormous workflows on thousands of GPUs. I should be, but I'm spending too much time with Nix packages. But how it should help is that, well, it's an example I mentioned on NixCon, and it was mentioned in, I think, Julie Evans's blog, or I don't remember which blog it was. I think it was Julie Evans. An example from the Facebook's logbook about training those huge language models, which if you just scroll to the very early dates and you start scrolling up, you see like days and weeks of people expressing their despair about issues like the huge run crashes for no reason, complaining about like some mismatches with the NVIDIA communications library, collective communications library, and people attempt things like, okay, maybe if we downgrade this library on the cluster, then things might suddenly start to work, and they try a bunch of stuff like that. And the way Nix could have helped them, I think, is that with Nix, you know exactly which version of this NVIDIA collective communications library you're going to use, because you can predict that, and you can predict where exactly this library is going to be located. You can predict that before the build happens, or at least in the current model until we've introduced content addressable derivations. You can predict in advance where exactly things are going to be. And the issue with NCCL in that case was that they built, say, PyTorch with one version of this library, and then there is the cluster where they impurely, in this dynamic manner, deploy a version of this library at some like /lib location, and that happens to be incompatible with whatever PyTorch has been built with, whatever PyTorch expects NCCL to be like at the like ABI level. With Nix, when you've built PyTorch and you're using PyTorch, it's not gonna look up this NCCL in /usr/lib. Instead, it's going to be a location like /nix/store, a very long hash which corresponds to this specific revision of this NVIDIA collective communications library, specific versions, specific Git checkout, and specific versions of its transitive dependencies. So this issue of NCCL incompatibility is just never going to happen.
Okay, so does that accelerate the whole workflow, and does it help with sharing your work, especially in research?
Well, it eliminates the need to manually figure out all of those runtime issues. Or it will eliminate if we use it more.
So what is it that you do in the Nixpkgs CUDA maintainers team? Are you solving these problems for everyone else? Is that how one can imagine it?
Well, I don't know. I'm mostly solving the problems I encounter, but they also tend to be the problems that at least some of the other people encounter.
What are these problems specifically?
Come again?
What are these problems specifically? So apart from some random deep down dependencies being mismatched.
Oh, well, okay. So at this point, I would say our CUDA support is still far from perfect in Nix packages. So from time to time, an issue might happen that there is some piece of Nix packages being updated, and suddenly a dependency for I don't know, something that depends on OpenCV fails to find package OpenCV because the way OpenCV's CMake config file is written, it expects to find some pieces of CUDA, even though it's not going to use them, and then we need to somehow propagate those. So people encounter very confusing build error messages, which are not really suggestive what the underlying issue is, and we're just trying to make the experience smoother and figure those issues out before Nix packages users face them, either in the form of getting more reasonable error messages or in the form of not getting error messages, preferably.
You talked about dependency pruning. Is that also something that you're doing? So for those who don't know, those packages tend to be huge in the multiple gigabytes.
Right. Yes. This is very high on our list of priorities. So for the context, when you use, say, PyTorch with Nix, when you say Nix shell Python with packages PyTorch, Nix is going to construct an environment that contains PyTorch and all of its runtime dependencies, or whatever, like within the model that we have, it thinks are the runtime dependencies. And just a couple of years ago, actually, I think a year and a half ago, if you did that, I think you would get a closure size of about 25 gigabytes, which would include, among other things, static libraries from CUDA toolkit, because, well, CUDA toolkit used to come in a single or in two, like, Nix store paths, and PyTorch at runtime still depends on those outputs, because it uses some of the dynamic libraries from CUDA toolkit, and they all come in a single pack because of the model we use. So naturally, PyTorch at runtime used to depend on the whole thing, including the static libraries, even though you obviously do not need those at runtime. So that used to be about 20 to 25 gigabytes. And over the last year or so, there has been a lot of work happening, a lot of it done by our hero Connor from Twig, but otherwise a group effort. If you do the same Nix shell Python with packages torch today, you're gonna get about 3 to 3.5 gigabytes. And the way this is achieved is, well, we split CUDA toolkit into many independent outputs. For instance, static libraries for each CUDA component go separately from the headers and libraries, so you don't depend on those at runtime. You can actually throw away most of the build closure after the build. But those are like just technicalities somehow imposed on us by the Nix model. It's to some extent a cost to pay that, yes, like in this particular aspect, you have to commit a little more work. But once that is done, again, things get much smoother.
Your mission statement on the team page also states that you're improving interfaces to customize these packages. Is that also something that's happening, that like people can reuse this infrastructure to build more of their own packages that are CUDA accelerated?
Right. Okay. So first, a word about the CUDA mission. This is a bit of a marketing talk, the whole thing. I think it was also written by Connor. I think it's great, and we definitely should do like marketing and outreach and all of that. But at the same time, like it sounds a bit pretentious, the whole thing. So with that in mind, yes, sure. That's also another thing we do. I think Nix packages today is probably the easiest way to build any, well, say, let's make it like narrowly scoped. If you want to build a C++ program, or maybe a native Python extension in C++ with pieces of code like with CUDA kernels, I think Nix packages is the easiest way to just get that running. And the reason is that, well, first of all, because you get all of those immutability and determinism properties, but also because the interfaces that Nix packages already offers are simply way too convenient to build C++ projects. And those interfaces, it so happens, they also just work for all of the CUDA stuff if you have done all of the previous work of putting things in where they belong. So specifically, that means that, okay, so say you had a CMake project. We'll forget about CUDA for a moment. You have a CMake project. It depends on maybe a ton of some other C++ dependencies, which are packaged also with CMake or maybe the exposed package config files. So you're going to have a CMake project. It has some find package, boost required, whatever. And then I think there is a conception that, like a good package manager is something like Cargo or NPM. It's so flexible. It's really great. But in fact, in certain ways, CMake is much superior to Cargo because it implements this find package interface, which is it declares a dependency, and then you can inject it. And you can use tools like VC packages to inject those dependencies. And it just so happens that Nix, well, specifically Nixpkgs and its CMake setup hooks are exactly that system which injects those dependencies. And it so happens that Nixpkgs is also the biggest repo which provides ready recipes for all of those dependencies, which you can clearly see on the repology graph picture, just looking at the scales. And then it happens that all of that applies to CUDA. There is a CUDA support in CMake has been improving a lot lately. There is this new find the CUDA toolkit.cmake module, which is maintained upstream, like by Kitware, I guess. And it supports exactly this layout we use, where every component of CUDA toolkit, like CUDA RT or like QBLAS, come from different locations. This CMake module just supports that. This is what it expects. And then since recently, it's also the way NVIDIA ships their CUDA toolkit in those separate components. So in your CMake C++ project, you say find the CUDA toolkit components QBLAS, and then you write a Nix expression where you say build inputs equals CUDA packages dot libqblas, and it's going to work out of the box.
That's quite slick.
Yes.
So what can be done today with CUDA support and Nixpkgs? Can you show us something maybe? If you can't show it, you can tell us.
Questions: what can be done and what can be shown? What do we begin with?
So yeah, let's tell us what is it that can be done today?
Okay. I'm sorry, I'm not getting the question. What can be done towards improving CUDA support? Or
what can you use it for already? What
Very
works?
good. I see. Okay, sure. Sure. We can give something a try. I think I already have the binary cache ready for a little demo, maybe. I don't know. If you can put my screen in the translation. Okay, so let's start with a cheesy example. There is this repo on GitHub with way too many stars, more than it. Okay, I'm not gonna say that. It's called like automatic something stable diffusion, which is it's something that is pretty hard to run in whatever environment. It's something that uses Git and pip at runtime in a very unorderly manner, and it's written in a way that you can, one of those Python projects that you can only run from their top level directory. And I would say that with Nix, it's actually not too hard to package and run those as self-contained apps. So for instance, you can do a simple Nix run. So Nix run is this command that comes with Nix Flake interface. I have a repo here which just contains a bunch of custom packages, among which is this stable diffusion thingy. Nix run is going to build this package, and it's going to find the main program in it. I think it's the web UI, and it's going to build it, and it's going to run it. And this particular attribute I used is going to build it with CUDA support, obviously. And well, now we have a web interface that I guess I need to shut the whole screen instead of the window now. Let's see if I can do that. Present, share screen.
Yeah, Robert has a comment for those who don't flake yet. Can be done with Nix run F.
Okay.
The command line interface is an independent experimental feature from Flakes. Okay, shall we show it?
Okay, this is going to take a moment. I'm migrating from Sway to Plasma, and it's not going too smooth. I'm maybe a little too used to Sway. Let's see if this works yet. I actually haven't touched this in a couple of weeks, but I suppose with Nix I can be sufficiently confident that it should still work, unless some of the impure stuff breaks. Okay, so this is what whichever model they use by default thinks about Nix. Oh, well, whatever.
It does work with one command, though, right?
Well, yes, we literally did a single Nix run. And the effort it takes to package it is, well, it's mostly just packaging its dependencies, which are a lot. I guess that's the let's see, dependencies. So this stable diffusion web UI is a simple build Python package, which is the routine we use for everything in the Python package set. It did require a bunch of patches, again, because they use Git at runtime, stuff like that. But aside from the patches, it's same as anything in the Python packages package set. And then actually, okay, it's actually even nicer than just packaging the web UI app, because I have this tiny tool that I use for projects like this, which a tool which basically takes a project that expects everything to be in the top level, all of the Python modules to be in the top level, which should look something like this. You're gonna have a Python module called modules and Python called,
we have to increase
Python
your font size.
Oh yes. Yeah. Let's see. Is that better?
Yeah, a lot.
Okay. So this is our victim, or rather our abuser. It's a Python project. In the top level, it has models and modules and many other generic names like embeddings. And there is an obvious issue with that, is that if you were to put this in the same Python path with like any other project like this, they all are going to have top-level models and the top-level modules and the top-level embeddings. So when if you put them in the same Python side packages and you try to import one of those things, eventually you are gonna run into nasty conflicts. But then we can automate a certain refactor. So if we look at the side packages of this package we've built, it doesn't contain models. It contains SD Web UI. And then all of the files inside of it are rewritten to use the prefix name. I've picked up this idea from Davhao, who picked it up from. There was another post on Nix's discourse about also renaming Python modules en masse to basically achieve the same thing we do with normal ELF binaries, like shared libraries, where we would enforce a binary, an executable, or a library to use a concrete revision of its dependency by putting its explicit absolute path in a run path, for example. So with Python, that's a bit harder because there is no ELF and there is no run path. But we can automate refactors like these. We can force things to use their own versions of dependencies and avoid conflicts. And we can feel relatively safe about that because of this like immutable model, and because on top of that we can just run tests. So and our tests are in a way significant in the sense that like if they pass once in one environment and one machine, we can be relatively confident they're gonna pass anywhere.
Yeah, thank you for this demo. What does it take to make these things happen? Are there particular obstacles to doing that kind of packaging work, apart from upstream projects being sometimes a bit tedious to work with?
Well, sure. Upstream issues are not the only factor. I think the biggest problem currently is, in fact, the lack of a single preferred CI and public binary cache for this kind of packages in the NixOS, Nixpkgs ecosystem. So this is a subject that has been around for a very long time, which is many people had asked or expressed their wish to have unfree packages like CUDA packages built and cached by Hydra, for the reason that it actually takes an enormous amount of compute to build something like PyTorch or, God forgive me, TensorFlow. Like for instance, on a Threadripper, building TensorFlow might take like 5 to 9 hours, depending on like scheduling. That is a lot, and for most of the users, that's prohibitively expensive. We currently have only like a small unofficial cache for this kind of packages, which is it's a cachex with some fixed amount of storage and garbage collection on, and we populate it with cache built on volunteers' machines. which is a very ad hoc and temporary solution, which in addition lacks any kind of reasonable security story. So the biggest effort is that we lack storage and compute and trust mechanisms to build and test this kind of packages at the moment, which is something we're hoping to figure out soon, TM. And well, okay, so the plan regarding this is that we've wanted for quite a while to write a NixOS Open Collective application. NixOS Open Collective is this effort started by Ryan Bizarios, which is there is an Open Collective page for NixOS, Nix packages related projects, which currently funds the Offborg refactor, the CI that hardens and tests Nix packages PRs. We want to have a similar page for not maybe even just CUDA packages, but in general for the scientific computing applications, I'd say. And that, so what I mean is that we don't just want to build packages with CUDA support enabled. Rather, we would also like to test and benchmark those extra variants of packages, and we would also like to have more flexibility than Hydra currently has with regards to, say, building with extra CPU architectures like x86 64 levels, AVX and SSE, which currently aren't built by Hydra for good reasons. The first of which is that we haven't proven that would lead to any significant benefits. But then HPC and scientific computing is this kind of a separate domain where proving this kind of stuff would be, or rather figure out where exactly those things matter is the kind of research you don't want to spend time on, because that effort is already expensive and it's easier to just build everything with presumably what should give you the best performance possible. Yeah.
I have so many questions about this. Great pointers here. Before we continue, let me remind the audience to send us your comments and questions. You are what makes this show come alive. As I wonder, so what about the scientific community and HPC community in general? I mean, as far as I can tell, natural scientists tend not to be super excited on average about programming because they just want to do science. Does this whole setup help them just get their work done more quickly?
What you mean by natural scientists? You mean scientists doing natural science, or
yes, or also natural-born scientists? I don't know, but yes,
no idea about those. Not the kind of science I've been doing. Okay, I guess I could say that Nix and Nix packages are probably underrepresented currently in this, say, academic kind of HPC environment. There are a few clusters that do use Nix. For instance, there is GRICAD in the University of Grenoble, I think, in France, which uses Gix and Nix for their HPC workloads, and they've recently held this workshop, and I've seen announcements about it on Twitter or Mastodon nowadays, I guess, where people express their surprise that, well, it actually works despite all of the obvious issues like small files on distributed network file systems, So that cluster, for instance, uses NFS with caching for the Nix store instead of the distributed file system, and apparently it just works. But then again, Nix is underrepresented. Even in that university in Grenoble, I think the deep learning related labs apparently use another cluster where they would do the more classic. They would follow the more classic approach where they have singularity images built using Docker, built from Docker images or something, and they would use conda. The same applies for the cluster we have here at Aalto. So in Aalto, we have our own cluster called Triton, and then on per application basis, people may have access to the national cluster and to the, I don't know, Northern European Lumi cluster, which is like this huge thing with AMD GPUs. And that basically, the way those are set up and configured at this point, it's not really convenient to run Nix there because, for instance, they don't even enable user namespaces. And for context, user namespaces is this kernel feature that allows you to, among other things, to do bind mounts on a, let's say, per process basis. You can have a process that is going to see as a different file system tree than the rest of your system. And this is important for using Nix in, say, this is important for using Nix in a scenario where you don't want to install it globally. So for instance, with Nix, you're going to have, you're supposed to have a dedicated immutable store, which we just by default assume to be always at /nix/store. And if you cannot create that directory, or you don't have permissions to modify anything in that directory, but you don't want to use Nix regardless, what you could do is you could choose any other directory, and you could use Nix with this bind mount, and there are tools that automate this, that basically that Nix process would see the store where it expects it to see, whereas the contents are stored elsewhere. You cannot do that on Triton today. In principle, you could. Maybe in future you would be able to, or maybe they at some point would even experiment with Nix. I have no idea. But the only way you could run Nix on Triton today is you'd have to use proot, I think, which is this another mechanism to basically achieve the same effect, but is way more expensive. You pay a lot of runtime compute cost for using that. So instead, if you wanted to use Nix, if you wanted to benefit from Nix in this kind of environments, what you'd have to do is you'd have to use Nix to build those, for example, singularity images, which is something you totally can do. And I actually started playing with that recently. So the same example I've shown with the stable diffusion bullshit. You can take that attribute and you can pass it to another function. It's called Singularity Tools MK image, I think. You pass it into that function, into its contents argument, and you build that, and you're going to get like exact same contents with all of the exact same dependencies, which are going to behave exactly the same way, but you're going to get them packed into an image. And then you can ship that to the cluster, and you say singularity exec SD web UI, I don't remember. And yes, you're going to get exactly the same thing. It's going to behave exactly the same. There's, again, you're not going to run into any of those issues where you think you're using one thing, but in fact it's using a different version of the same thing. So none of that is going to happen. And you can reproduce that a year later.
Yeah, that's definitely so. We had this talk from Konrad Hinsen last year in the summer of the Nix public lecture series, where he essentially described just that. So science usually picks up from work from years in the past, and that is definitely relevant. Let's talk more about hardware support and for GPU acceleration in general. What else is out there? So CUDA is by far, as you said, not the only platform. What's the state in Nix packages? Is there something else that one can use if you don't have NVIDIA hardware?
Well, I mean, yes, sure. First of all, like CUDA hadn't always been the first option for CUDA doesn't do anything fundamentally too different from what, say, OpenGL like shaders do. So in principle, you could use OpenGL to multiply matrices. You can use libvulcan to do the same thing. You can use OpenCL. Difference is going to be like the build and deployment process. For instance, like certain things that with CUDA happen at actual build time are going to happen later at runtime with, for example, OpenCL. But then in practice, I guess the answer is that if you want to do all of the same things, but you don't want to buy an NVIDIA GPU and get all of those issues with driver incompatibilities, CUDA toolkit driver kernel module incompatibilities, and you prefer to just invest in AMD, you are going to use the ROCm framework, which is it's a tool chain and collection of libraries that basically, to some extent, try to mimic the same interface as CUDA does, but it's largely developed by AMD, I guess, and it works with AMD GPUs. And you can build PyTorch or TensorFlow with ROCm support, and you can do that with Nix packages as well. So, for instance, what's going to be different is that instead of saying import Nix packages config.CUDA support equals true, you're going to say import Nix packages config ROCm support equals true. And then you take the same Python with packages torch attribute, and you're going to get PyTorch, and that's going to just work with NVIDIA GPUs. Wow, actually, it's going to work even smoother than with CUDA, because with CUDA, there is like this extra step you have to make. You have to configure your host system appropriately, which is something we automate with NixOS, but something that is a bit less reliable with other operating systems. And the issue is that, well, the issue is the business decisions that NVIDIA makes or is forced to make. I have no idea. But the issue is that when you build a project that uses CUDA toolkit, it's going to try to open this special library called libcuda.so, which is the user space driver for CUDA. And there are certain constraints, range constraints on which CUDA toolkits are compatible with which user space drivers, but that is only the beginning of the issue. The real issue is that your libcuda.so is locked to the exact revision of your kernel module, the like .ko modules that come with your kernel. So basically what it means is that this library has to come together with your kernel, and it's got to be the same exact version.
That is something that you don't get on vanilla systems, but which you can configure on NixOS.
Yes, well, I mean, on the vanilla FHS systems, you also install this library together with the driver. That's, well, I mean, I think that's exactly the same in pretty much any environment. But then for us, the problem is that we like to take control and make the whole thing deterministic. So when we link a shared library, we like to link the exact version of it. And it just doesn't make sense to do that with this libcuda SO. So instead, we do a special trick to link it impurely. Like we make an exception for this driver, user space driver library. And then, well, okay, sure, that still works. And you don't even notice this if you use NixOS. And if you don't use NixOS, you're gonna use maybe Numptide has this repo called Nixjailhost, which is a flake that you can use that just you can wrap any command you want to run into this Nixjailhost, and it's gonna figure out where in your Ubuntu system this driver is deployed, and it's gonna set up things appropriately so that it all still works. But the thing is, you don't have to do any of those hacks if you use ROCm, because they don't make the business decisions that NVIDIA makes, and there is an open source kernel module and basically all of the driver libraries that you have with ROCm, you can link directly, and they're going to be compatible with a range of kernel modules, which is great.
Oh, what's the current support in terms of hardware? Is there a list of hardware that is compatible with the approach in Nixpkgs? Is there something that we can look up?
This approach meaning the ROCm stuff, or what? I mean,
generally for GPU support.
Well,
how does one figure out if a particular setup will work?
This is all determined by upstream. I mean, like, there really isn't anything special about those libraries and modules in NixOS or Nixpkgs, except that they just work. They give you more of this hands-free experience. So if you want to figure out whether you can use the Nixpkgs CUDA packages with a particular NVIDIA GPU, you just open the NVIDIA datasheets or specifications. You see, like, okay, which does it come with any of the CUDA kernels? Which CUDA capabilities? Like, what is the CUDA microarchitecture it implements? And then you see if that is supported by any of the CUDA toolkit releases that come with Nixpkgs, and the CUDA releases that come with Nixpkgs are like whatever is not end of life as determined by NVIDIA. So you just set the right CUDA capabilities and the right CUDA release, and it's going to work.
Okay, we have at least one user question here, which I would put a bit to the end, because I would like to know, does NVIDIA or AMD actually support these efforts? Because that does help them to sell their products, right? So if a university buys 1,000 GPUs and they can run them on a whim, do they support you to any extent?
Not at this point. At this point, we don't really have any formal, say, collaboration with anybody. We have like some NVIDIA employees involved in packaging that just help us out with some random questions. And we've been trying to contact NVIDIA, for instance, regarding their licensing issues, which is like they have this end user license agreement for CUDA, which like it's phrased in such a way as if it intends to permit redistribution of those binaries, but then it puts some extra constraints which basically make it impossible to redistribute them, and it's a bit problematic. And we know that the way people have approached this is that NVIDIA has made special private exceptions for certain projects like Conda Forge or Julia or whatever. So we'll need something like that for Nixpkgs as well.
That plays into the whole caching issue, right? So that the build-through products can be...
Exactly.
Mm-hmm. So I'll read power user's question here about optimization. So detailed questions about something that we talked prior. When you talk about optimizing packages, are you talking about link time and profile guided optimizations or -O3?
Okay, so I was mostly referring to enabling the microarchitectures, like say enabling things like x86 64 v3, or enabling like specific march platforms that we expect to run our packages on. Link time optimization, sure. We're somewhat hesitant towards trying profile guided optimizations with Nix because that affects determinism. It's like when we enable something, we still would like to be able to prove that it does have the effect we intended to have, and like it has it reliably. Yes. And then I think like O2, O3 are not an issue. You probably can just enable those. Sure.
So what are your plans for the future, and how can one help and support the maintainers of CUDA and GPU acceleration packages in Nix packages? Where do you work? How do you contact you? And yeah, how to help?
Okay, so first of all, there is a matrix chat dedicated to CUDA issues in Nix packages.
We'll post the link after the show.
Sure. Sure thing. You can drop in the chat. You can ask questions. You can complain about stuff. You can link the PRs you're opening. Then on GitHub, there is a project board specifically for CUDA-related efforts, which we've been basically using to dump our brains, and well, we use it for synchronization. Just when somebody's changing structure of stuff in any significant manner, I guess we try to open a ticket there and explain why it happens, and like what is the end goal we're moving towards. That also lists, like, I guess the good first bug kind of issues as well, if I remember correctly. I will post the links. And there is also a CUDA team page on nixos.org, which actually contains a lot more information than I just said, and it contains all of the links. I think it was community Nixos community teams CUDA team. Yep. So this contains the links to the chats, to the project board down here. It also explains how to whom to contact to help financially. When we finally get around to write the Open Collective application, we're gonna push a link to the project onto this page as well. This is where you would be able to fund the CI and the binary cache. I think that's how you start.
Well, thank you very much for being my guest today. The next show will be tomorrow, Friday, December the 8th at 19:30 UTC, where we will meet Aalto University, the inventor and principal author of Nix, and Ron Efroni, both on the NixOS Foundation board. And the topic will be keeping the lights on, news from the NixOS Foundation. Thank you very much, Sergei, for being here today. Thank you, everyone, for watching. And until next time with the 2023 Nix Developer Dialogues. Bye-bye.
Thank you, Valentin. Thank you, everybody. Bye.